Okay, let's look at how to find the expectation value of the total angular momentum for this electron state. First up, we have the question itself. We are given the normalized wave function for an electron. You can see the form there. It's psi of r vector, which equals r of r multiplied by this combination of spherical harmonics and spin states. We are told that YLM are the standard normalized spherical harmonics, and chi plus and chi minus represent the two spin states, with eigenvalues of plus or minus 1 half h bar for the SZ operator. Our task is to find the expectation value of the z component of the total angular momentum in this specific state, and we have four options presented. To find the expectation value of any operator O, we use the familiar formula shown. The given wave function is a product of a radial part and this angular and spin part, which we denote as psi ket. We can quickly verify its normalization by summing the squares of the coefficients. 3/8 plus 5/8 equals 1. Since the total wave function is normalized, we can focus solely on this angular spin part for calculating the angular momentum expectation values. We need the expectation value of the z component of the total angular momentum, which we write as Jz. Remember, the total angular momentum operator J vector is the sum of the orbital angular momentum L vector and the spin angular momentum S vector. So its z component Jz is simply the sum of the z components of orbital and spin angular momentum Jz equals Sz plus Sz. Now it's helpful to know the eigenstates of Lz and Sc. The spherical harmonics YLM of theta phi are the eigenstates of Lz. When Lz acts on YLM of theta phi, you get the eigenvalue mh bar times YLM of theta phi. Here m is the azimuthal quantum number. For the spin states, chi plus and chi minus are the eigenstates of Sz. Sz acting on chi plus gives you the eigenvalue plus 1 half h bar times chi plus. And Sz acting on chi minus gives you the eigenvalue minus 1 half h bar times chi minus. Let's analyze the first term in the wave function's angular and spin part. This state is a combined eigenstate of both Lz and Sc. For the orbital part, the Lz eigenvalue is 0. For the spin part, the Sc eigenvalue is minus 1 half h bar. Since Jz is the sum of Lz and Sc, and this state is an eigenstate of both, it is also an eigenstate of Jz. The Jz eigenvalue is simply the sum of the individual eigenvalues, which is minus 1 half h bar. So this first term corresponds to a component that is an eigenstate of Jz with an eigenvalue of minus 1 half h bar. Next, let's analyze the second term in the wave function's angular and spin part, the square root of 5 over 8 times y11 of theta phi chi plus. We look at the state part y11 of theta phi chi plus. This state y11 of theta phi chi plus is also a combined eigenstate of Lz and Sc. For the y11 part, the Lz eigenvalue is mlh bar. Here ml is 1, so it's 1 times h bar, which is h bar. For the chi plus part, the Sz eigenvalue is msh bar. For chi plus ms is plus 1 half, so it's plus 1 half h bar. Applying Jz equals Sz plus Sz to this state, Jz acting on y11 of theta phi chi plus equals the sum of the eigenvalues multiplied by the state 1 plus 1 half times h bar times y11 of theta phi chi plus. This simplifies to 3 over 2 h bar times y1, 1 of theta phi chi plus. So this second term corresponds to a component that is an eigenstate of Jz with an eigenvalue of 3 over 2 h bar. Now let's calculate the expectation value of Jz for our state psi. As shown on the slide, psi is a superposition of two orthonormal eigenstates of Jz with specific coefficients C1 and C2 and corresponding eigenvalues E1 and E2. The expectation value is calculated by summing the probability of being in each eigenstate. That's the absolute value of the coefficient squared, multiplied by the eigenstate's eigenvalue. Following the steps shown, we substitute our known values, square the coefficients, and perform the multiplications. We then add the resulting terms. As you can see, they share a common denominator. This leads us to 15 minus 3 over 16 times h bar, which simplifies to 12 over 16 h bar. Finally, we simplify the fraction 12 over 16. Both are divisible by 4, so 12 divided by 4 is 3 and 16 divided by 4 is 4. So the expectation value of Jz is 3 over 4 h bar. This result matches option number 2. Therefore, the expectation value of the z component of the total angular momentum in the given state is 3 over 4 h bar.